Snausene. Good morning, fellow mathematicians. Welcome back to Papa Flemmy's Integral Week. And we are back at it again with this sexy boy right here. I already made a video on 4 ways to integrate it. I've got 7 more ways to integrate it, actually, but we are going to do 3 or 4 more ways today. Be prepared for it. And it's going to be quite nice. Okay, at first we can rewrite e to the x a little bit, because we can split it up in an odd and even function. They are called the hyperbolic cosine and the hyperbolic sine. So this is nothing else than the integral of dx over. So I'm going to call them cos and sinh. So that's cos of x plus sinh of x. And there's another nice identity. We can rewrite 1 as cos squared minus sinh squared. So this is positive cos squared of x minus sinh squared of x. That's a damn long expression, my boy. Okay, and you might notice it, or you won't, but this is the difference of 2 squares, so we can break this up even more. So we can rewrite this as the integral dx over. So this is cos of x plus sinh of x, and then positive. So the first part is cos of x minus sinh of x, and then times, and this is cos of x plus sinh of x. I've never seen such a long denominator in my life before, mate. And the great thing is, cos plus sinh is a common factor on, we can rewrite this. Right here, this is one time this term plus this term. So we can factor out this expression right here. So that's now the integral dx over. So this is at first cos of x plus sinh of x, and then times 1 plus cos of x minus sinh of x. And here's another great thing we can do. We can multiply this whole expression by a 1 and it won't change anything. But what exactly is a 1? Well, a 1 is nothing else than cos of x minus sinh of x over cos of x minus sinh of x. And I hope you agree with me that this is true, that we can do that. Under the condition that this isn't equal to 0, of course. And the nice thing is, if we multiply this term with this term, this will give us exactly this term, which is just a 1. So what we end up with now is just the integral of cos of x minus sinh of x over 1 plus cos of x minus sinh of x dx. And here's the crazy thing, we can now introduce a u substitution. So let u equal to our denominator here. 1 plus cos of x minus sinh of x. And when we differentiate that, we end up with du is equal to cos becomes sinh and sinh becomes cos. So this is sinh of x minus cos of x dx. And the great thing is, this is nearly our whole expression right here. We just have to factor out a minus 1, and that would be our original expression. So let's conclude what we get. We now end up with the integral of minus du over u, and this is nothing else than minus the natural log of u, and well, that is minus the natural log of, and u was this expression right here, so this is 1 plus cos of x minus sinh of x plus c. And then we are done. That was quite a long way, but we've reached our finish, and in another video, this will take quite some time, I'm going to show the equivalence of all the answers we get today. Alright, next one. So for the next one, we are going to get a little bit more creative. We are going to use a little bit more trigonometry on this one. So let's at first introduce a new substitution. So let e to the x equal to tangent squared of phi. So when we differentiate that, what would we end up with? So that's e to the x dx equals 2. And this differentiated, that's not too hard. That's 2 times secant squared of phi tangent of phi d phi. We are defying the system of mathematics once again. And now we can divide both sides by e to the x because it's not equal to 0. And remember, e to the x is nothing else than tangent squared of phi. So what do we end up with? Dx is nothing else than 2 times secant squared of phi tangent of phi over tangent squared of phi d phi. And well, this and that we cancel out, and that's our final expression for dx. So we can plug everything in, so we end up with, okay, so this is 1 over tangent squared of phi plus 1 at first. So that's quite nice. And what else do we have? We got this expression now, so that's 2 times secant squared of phi over tangent of phi d phi. And if you're familiar with some identities, this expression right here in the denominator is just secant squared of phi. So this and that will actually cancel out. We can bring the 2 to the outside, and we end up with 2 times the integral of d phi over tangent of phi. But what is tangent of phi? Tangent of phi is sine over cosine, and since it's the reciprocal, we have to turn it around. So we end up with 2 times the integral of cosine of phi over sine of phi d phi. And we can actually integrate that because we can make another substitution, for example, u in this case. So let u equal to sine of phi, and we will end up with du equals to cosine of phi d phi. Great. And cosine of phi, d phi is just our denominator here in this case, this term. So we end up with 2 times the integral du over u. We know how to integrate that. That's just natural log. So that's 2 times natural log of u. Well, but what is u? U is nothing else than sine of phi. Okay, but we are not done yet because we are still in the phi world. We need our e to the x somehow. We need to get back to our x world, like black pen, red pen would say. Okay, so how can we go back in this case? Let's take a look at this expression right here, and I'm going to do this on next chalkboard, I guess. I just noticed that we don't even need to do that on next chalkboard because what we can do, I'm sorry for that, I was kind of confused. We can take the square root right here on both sides, and then we can use the inverse tangent. So phi is nothing else than the inverse tangent of the square root of e to the x. So actually we end up with 2 times the natural log of the sine of the inverse tangent of square root e to the x plus c. And now we are done with this one. To the next one. So this next one is going to be a fun ride. Materia Sacra once wrote this as a comment, and I think that's an absolutely awesome way. So, just like before, we can multiply a fraction by a 1 and it won't change anything. We could multiply everything by 1 in the field of real numbers. So we could, for example, multiply by e to the minus x over 2 over e to the minus x over 2. And now we can distribute everything into everything, and what we end up with is the integral of e to the minus x over 2 over e x over 2 plus e to the minus x over 2 dx. And now we want to take a look at the integrand right here, because we have to manipulate it a bit algebraically. Okay, so what is e to the minus x over 2 over e x over 2 plus e to the minus x over 2? So what we could do at first, we could expand this fraction by a 2. And it won't change anything. So we can do that. That's just multiplying it by 1 once again. But what is 2 times this expression? Well, this is just this one right here plus itself. So plus e to the minus x over 2. And it wouldn't hurt us at all if we would add a 0 to this whole thing. It wouldn't change anything. But what is a 0? Well, a 0 is nothing else than saying it's e to the minus, e to the x over 2 minus e to the x over 2. So we can add something and subtract it right away and it won't change anything. And here's the nice part. We can also factor out this 2 right here and we can break this fraction up into 2 parts. So what is that? This is 1/2 times. So there's the first part. So that would be e to the minus, e to the x over 2, let's put it that way, plus e to the minus x over 2 over e to the x over 2 plus e to the minus x over 2. And also, well, let me do something real quick. We can factor out a minus on this one. So minus e to the x over 2 minus e to the minus x over 2 over e to the x over 2 plus e to the minus x over 2. And this right here is obviously just a 1. And this right here, maybe you notice identity, but this is just the hyperbolic tangent of x over 2. Like I said in the beginning, that's going to be a fun ride, and it really is. It's awesome. So that's a nice way. And now we can plug everything into here and see what we get. So we now have the integral of, so this is 1/2 now, so that's nice. 1/2 dx, I'm going to use the linearity of the integral and split it up, minus the integral of, I'm bringing the 1/2 to the outside, the hyperbolic tangent of x over 2 dx. And we are nearly done. We know how to integrate this right here. This is just x over 2. And we can rewrite this integral right here as the hyperbolic sine of x over 2 over the hyperbolic cosine of x over 2. And how do we integrate that? Well, let sum u equal to cos x over 2. Well, when we differentiate that, we end up with du is equal to, we have to bring this 1/2 to the outside. So this is 1/2 times sinh x over 2 dx. So that's nice. Because we know 1/2 times sinh of x over 2 is just our du in this case. We also have this dx. So all in all we get x over 2 and then minus the integral of du over u. And this is just x over 2 minus, okay, so this is minus the natural log of u, okay, and this is x over 2 minus the natural log, but what is u? It's just this expression right here. 1/2, no, it's the cos of x over 2. I'm sorry. Plus some constant c. So that's a great solution, and for the last one, yeah, now for the last one. Okay, let's get serious on the next one. And with serious, I actually mean serious. So at first, let's remember what the geometric series looks like. So we get 1 over 1 minus x is equal to the sum from, let's say, n equals to 0 to infinity of x to the nth power. So this right here is the geometric series, and we can actually manipulate this one right here to look like that. So this is the integral of dx over 1 minus e to the x. And now we use this property right here without any restrictions. So this is the integral of the infinite sum from n equals to 0 to infinity of, okay, what do we get now? This is just minus e to the x to the nth power dx. And now we have to break this apart a little bit because we have a minus 1 in here. That's an alternating series right now. So this is the integral of the infinite sum n equals to 0 to infinity, minus 1 to the nth power, e to the nx dx. Okay. How can we proceed? Well, we can interchange this integral sign and this summation without any restrictions, and we can also bring this minus 1 to the outside. But there's a little problem with it, a huge problem. If we would just bring something to the outside and then integrate it, follow my thought process, if we integrate that, this exponential function, we would get 1 over n times e to the n x. Okay, but we start our index at n equals to 0, and this is not good, my boys, because we would get 1 over 0, and this is not defined properly. So what we do, we are taking out the first part of the sum when n is equal to 0. So let's rewrite this. This is now the integral of, okay, taking out the first part, so that's minus 1 to the 0th power times e to the 0 times x. And then the next one, positive, and now the sum from n equals to 1 to infinity of minus 1 to the nth power e to the nx dx. And this right here is just a 1, and we can use linearity of the integral and break this apart. So our first one is just the integral of dx, and this is indeed just x when we integrate it. Okay, and then positive, bringing the sum to the outside now, from n equals to 1 to infinity, and also this minus 1 to the nth power. And we now only have to integrate e to the nx dx. And what do we end up with for now? This is just x plus the sum from n equals to 1 to infinity of minus 1 to the nth power and e to the nx over n dx. No, not dx, without a dx. But we need some arbitrary constant c. And how can we proceed now? The bad thing is we've got an infinite sum here, but we can work with it because this is representing the natural log on the next blackboard. Keep in mind what the Taylor series or Maclaurin series expansion for some ln 1 plus x is. So what is it? Let's take a look at it. ln of x plus 1. We can represent it in a little bit different way. This is del n of 1, which is just 0, so that's nice. This is 0, and then negative or positive, whatsoever, the infinite sum from n equals to 1 to infinity of minus 1 to the n plus 1, minus 1th power, doesn't matter. Let's take minus 1, and then x to the nth power over n. And well, this right here is nearly everything we need. The only thing is we have an to the nth power right here, so that's not good. How can we fix that? We can factor out a minus 1, and we would just end up with, with this right here, with the natural log. So let's conclude. This is x minus the infinite sum, not using the indexes now, minus 1 to the n minus 1th power, e to the x to the nth power. Let's rewrite this like this here, over n plus c, and all in all this is just x minus the natural log of 1 plus e to the x plus c. And we know that this is true. If you like this video, please like and subscribe, recommend me if you like. And well, if you want to support me a bit more, take a look in the description, there will be a link to my Patreon. And up until the next video, have a flammable day. See ya.
Hallo Mama.